It's an anomaly. Measurement outcomes fail to be predicted by the conventional theory.
I met with physicist turned philosopher Ruth Kastner, who developed a formulation that claims to solve not just the measurement problem, but also retrocausality, non-locality, and the unification of quantum theory with gravity. Her transactional formulation, which builds on Kramer's work, asserts that space-time itself is not fundamental, but emerges from what she calls the quantum substratum, not a realm of probability, but a realm of possibility. Questions we explore are: what's the role of retrocausality in quantum mechanics, also known as time travel? Does consciousness play a role at all? What about free will? And can you make gravity consonant with quantum theory without so-called quantum gravity? Ruth, I'd like you to paint a clear picture of what the motivation is behind the transactional interpretation, especially its so-called retrocausality. And the way that I'd like you to do this is to pick some standard account in quantum mechanics or quantum field theory, discuss why this standard account seems to make sense to most physicists, then explain why it doesn't actually make sense, and then explain why the transactional interpretation fixes or resolves these problems.
Sure. Okay. So, what got me interested in the transactional interpretation is basically my dissatisfaction with the conventional theory's inability to describe what counts as a measurement. So, and this is, of course, the measurement problem of the conventional theory. So, the problem with the conventional theory is that it does not have any kind of tools or anything in the formalism that lets you distinguish between just a kind of an interaction that would not trigger an outcome and a kind of interaction that counts as a measurement. So the theory itself, the conventional theory, just doesn't have anything that lets you say that a measurement occurred and an outcome happened. So what TI does is, and I can get to that in a little while, but it remedies that. And just to kind of to elaborate on the measurement problem, I mean it's illustrated by the Schrödinger cat experiment, and this was actually a thought experiment that Schrödinger came up with because he was dissatisfied with the standard theory's inability to explain what counts as a measurement. So the basic the Schrödinger cat experiment that people are so familiar with, but that maybe perhaps don't quite understand the point of it, the import of it, is what is called a reductio ad absurdum of the standard theory, of the conventional theory, that illustrates a problem, a weakness of the conventional theory. So the basic thought experiment starts with an unstable atom, which is a quantum system that you can represent as being in a superposition of having decayed and having not decayed. So at some point, at some time, this thing's going to send out a little decay particle from its nucleus, but its description is a superposition of having decayed, having not yet decayed. So the standard theory, all it lets you do is create correlations between states. So if you bring in a Geiger counter, like you want to measure, well, has it decayed yet? You use a Geiger counter, but according to the conventional theory, the Geiger counter has to be described by states that will then be linked up with the superposition of these two states of the atom. And I kind of think of it as the atom having like two train engines. The having decayed train engine, the undecayed train engine, which is like a superposition of states. So when you bring along the Geiger counter, if it's going to be correlated with these states, it then has to acquire these two states corresponding to that atom, which are triggered Geiger counter and untriggered Geiger counter. So you've got already a situation where the theory doesn't tell you that a measurement happened. It just creates a superposition, a larger superposition of these little trains. And all that happens in the conventional theory is you keep adding train cars. So if I want to say, so this is what Schrödinger kind of exploited. And he said, well, okay, then when I get bigger and bigger, I'm still going to be getting just states that are like train cars. So, for instance, okay, I don't know, I'm going to take a cat and see what happens when I link up a cat with all this stuff, and we're going to, in order to affect the cat, I'm going to say there's a vial. He said poison gas, but I'm going to say sleeping potion.
Sure.
So there's a vial of sleeping potion that can be just attached as a train car to these states. So if the Geiger counter is triggered, then supposedly that gets a little hammer to smash this vial, and so the vial is broken, releases the gas. So we've got broken vial that is now correlated with the decayed atom, but then we've got an unbroken vial state that is correlated with the undecayed atom, and then we've got to bring it in a cat. The cat is just another train car according to the conventional theory. So on one hand, the cat is asleep; on the other hand, the cat is awake. And again, you've just got a superposition of trains. And you supposedly got a cat in a, suspended between awake and asleep, and we never see that. And so it's an illustration that you can't get a measurement outcome from the standard theory. So what the transactional interpretation does is, in a nutshell, and we can elaborate, is it uses a different theory of the way fields behave so that, and this is, it kind of seems radical, but this theory has various names. It's been called the Wheeler-Feynman absorber theory. It's been called the direct action theory of fields. And it actually involves not just an emission. The conventional way of looking at field propagation sees things like something generating a field, something radiating. That's understood. But what happens in this direct action theory of fields is that under certain well-quantified circumstances, the other systems that we think of as absorbers, potential absorbers, are active, and they are actually generating a field that corresponds in a way to the emitted field from emitters. And this field has a strange character in that it's a so-called advanced field, meaning that it's path-directed. But when you look at the formalism of the way the fields behave in this theory, you get actually a very nice formal correspondence with certain kinds of, long story short, you get what's called a transaction, so that you get not just a field being emitted, but a confirmation, what John Kramer, who was the originator of the interpretation, called a confirmation wave. And you actually get this kind of connection, this interaction that clearly defines that a measurement is occurring, that it has the formal character that a measurement is occurring, and it breaks these superpositions. And it gives you the kind of formal objects that we call projection operators that correspond to outcomes, to clearly achieved outcomes. But they each have a probability, and that probability turns out to correspond to the so-called Born rule. So it very nicely, it yields a way that, under certain clearly quantified conditions, you are overwhelmingly likely to get this kind of confirmation, and together with this offer wave, confirmation wave, and you get a transition from the suspension in a superposition to a state where we have some clearly defined outcomes. And then they will not all happen, but they are clearly distinct from just a superposition. They're distinct theoretical objects. And then you can talk about, maybe symmetry breaking. You could say, the theory will not tell you which one of those is actualized, but it does tell you that indeed a measurement interaction occurred, so that, you can say that I now know, I can now say under what conditions I get a measurement interaction. So that's what I like about it.
So is the measurement problem twofold? One, what counts as a measurement? And then two, why is it probabilistic? Are those two separate questions?
You could say that. There are different ways of characterizing the so-called measurement problem, or the measurement, what counts as a measurement, and the different features of it. Von Neumann kind of pointed to two stages of measurement, which I kind of had covered just now, but to make them more precise. the initial stage of measurement is the transition from this superposition state to this state of clearly defined, different possible probabilistic outcomes. And that's called a mixed state. So there's that transition. And then there's what we could call the second stage would be what we could call a collapse from that collection of possible outcomes, weighted outcomes, to the one outcome that we see. So you can think of it as two stages in that way. But the two stages correspond to, I think, roughly what you just said, that the first stage corresponds to, okay, now I can say that a measurement really happened. That I can now use to apply my Born rule to the probabilities of these different outcomes. But then, again, the theory won't tell you, well, why did I get this one and not the other one? But that's because the theory is genuinely indeterministic. It's genuinely probabilistic, which is puzzling. We'd like to, our Western conventions are that science has traditionally demanded kind of a causal, mechanistic, deterministic account from point A to point B, and that the idea being that if you don't have that, there's something missing in your explanation. But I think what a lot of people are now, more and more understanding that quantum theory is not going to conform to that expectation because it is genuinely indeterministic.
Can you give another account or another picture? Like, let's say we have an electron and there's a Feynman diagram, an electron coming here, and they emit a so-called virtual photon, and then they move apart. What does that look like in the transactional interpretation? You mentioned absorbers, yes, offers, emitters, confirmations. So what is offering? What is confirming? Is there a clear distinction? Is it the electron? Is it something more fundamental? Explain.
Sure. So actually, in a Feynman diagram, what you kind of referred to there is really a kind of a scattering process that does not correspond to the offers and confirmations. So this is at a subtler relativistic level where, when you've got, two electrons coming in and connected by this virtual photon and then going out, that's actually just one term in the so-called perturbation expansion. So there are many contributions and many ways that the field interacts. But at that level, these are virtual photons. So the key point is a virtual photon is kind of a way of referring to the aspect of the direct action theory that is, for physicists watching, it's the time symmetric propagator. So that is not an offer or a confirmation. It's an influence. It's a level of the field interaction that in the direct action theory is always present among charges. So really the term charge just means being connected to other charges with this so-called virtual photon connection. It's not a measurement. It's not a measurement interaction. It's a correlating type of interaction. So there are two levels. So that's a nice question because it allows us to get to this subtler point that as I've developed the transactional interpretation into the relativistic domain, it becomes clear that there are these two levels of the field behavior. So that when you have something like free electrons, they do not have a situation where, if they're totally free electrons, they would not be able to toss a real photon from one electron to another because that would not satisfy the conservation laws. So that under that situation, a transaction is just not permitted because it has to satisfy the conservation laws. However, when you have something like an excited atom, and then you have an unexcited atom, then you have a situation where they can interact in a way that a real photon could be transferred from the excited atom. It could drop down to a lower energy state, and then that ground state atom could absorb that real photon and pop up to a higher energy state, and energy conservation would be satisfied. And under these conditions, you can have a quantitative time-dependent probability that these guys are going to engage in a transaction, meaning the excited atom is going to generate an offer wave. The unexcited atom is going to generate a matching confirmation wave. And this is actually the object that corresponds to a real photon. And upon that kind of interaction, a real photon, which means it's on shell, which means it's truly massless and only transversely polarized, will go from that excited atom to the unexcited atom. And then it will be excited. So there are these two possible kinds of interactions. The latter one is a measurement. That's what counts as a measurement. And that's why you don't need to refer to observers. You don't need to say, oh, well, I need to, posit some outside observer to say that something really happened, some clear outcome event happened. Because in this picture, the formalism gives you the fact that an emission event occurred at some time t, and an absorption event occurred at some time t. And these can have observable consequences, even if no one was around, happened to be around to see them.
As you know, on Theories of Everything, we delve into some of the most reality spiraling concepts, from theoretical physics and consciousness to AI and emerging technologies. To stay informed in an ever-evolving landscape, I see The Economist as a wellspring of insightful analysis and in-depth reporting on the various topics we explore here and beyond. The Economist's commitment to rigorous journalism means you get a clear picture of the world's most significant developments, whether it's in scientific innovation or the shifting tectonic plates of global politics. The Economist provides comprehensive coverage that goes beyond the headlines. What sets The Economist apart is their ability to make complex issues accessible and engaging, much like we strive to do in this podcast. If you're passionate about expanding your knowledge and gaining a deeper understanding of the forces that shape our world, then I highly recommend subscribing to The Economist. It's an investment into intellectual growth, one that you won't regret. As a listener of TOE, you get a special 20% off discount. Now you can enjoy The Economist and all it has to offer for less. Head over to their website, www.economist.com/TOE, TOE, to get started. Thanks for tuning in, and now back to our explorations of the mysteries of the universe.
Even if no one was around, happened to be around to see them.
Most of the time when people in the lay public, when they think about quantum mechanics, if they're even thinking about quantum mechanics, they conflate observers with measurers. So is that okay? Are they distinguished in your view?
Yes, they are distinguished. They need to be distinguished. And you can't really blame the public for doing that, because that is something that physicists have been doing since basically von Neumann, and maybe earlier. And it's just a symptom of this problem with the conventional theory, where you cannot define measurement from within the theory. And so then the convention became to just say, I'm going to just say, okay, when there's some outside observer who comes in, then I'm suspending quantum theory, and I'm just going to put in my measurement transition by hand in an ad hoc way. So it's a hand wave to some conscious observer outside the theory, where you just cut. In fact, Heisenberg called it a cut, and it's arbitrary in the conventional theory. And people have actually even used this as well, this is nice, I can do stuff with this. I'm like, no, it's just an ad hoc failure thing that you're doing, because it's a hand wave to what counts as a conscious observer. And that's the whole point of the Schrödinger cat experiment, right? Because Schrödinger was dissatisfied with that, sort of equating measurement to observation, because he could say, well, isn't the cat conscious? What is it? What counts as something conscious? And philosophy has no principled way of saying, that one thing is conscious and another thing isn't. So it gets you into this kind of thorny, ad hoc hand waving land. And so what I do, and what I've done in my books, and I do it on my blog, I have a blog post that addresses this, that I think there's one post where I say, there is measurement when you're observing, or but not but you can but not all measurement is observation. Measurement in the sense of an outcome happened, right? So the term is inherently ambiguous and problematic because observation sounds anthropomorphic and intentional and so on. But and observation is important in science, and of course we do observations, and that's important. But the issue about the term measurement in quantum theory is, did an outcome occur or didn't it? That's the key. And the conventional theory cannot answer that. You cannot answer that from within the theory. You can never say an outcome occurred. It will not let you say that an outcome occurred if you're being strict about it. So that's what you get. You get outcomes, whether or not someone was there to see it. So like in TI, you get, a tree did fall. I mean, it doesn't need you to be there to help it fall, or it doesn't need this sort of like, there's almost a hubristic component to it where, oh, we must have someone observing something or it didn't happen, and that gets into anti-realism too. But in TI, you can say from within the theory that a measurement interaction happened. Here's why. Under various quantified circumstances, here's where you are overwhelmingly likely to have a measurement transition where an outcome will occur, whether or not there happens to be somebody there to observe it.
So you said that it's likely that there's going to be a measurement transition.
Mm-hmm.
So I understand that the measurement itself is not determined. Sorry, that the outcomes of the measurements are not determined, but the fact of a measurement is also probabilistic?
Correct. And so this corresponds to decay rates in the conventional theory. So one way they link up is that in the transactional interpretation, when we're calculating a decay rate by this conventional theory, we're also from the standpoint of TI, the transactional interpretation, we're calculating the probability that at any particular time t, a measurement transition will occur. Because in order to get a decay, like I said before, you must have the proper circumstances, but those are probabilistic, and it may or may not happen at a particular time t. So again, that's kind of a deeper level aspect of the probabilistic character of quantum theory. Having said that, however, for situations of ordinary macroscopic experience and the kinds of phenomena, like every second of every day, we're seeing determinate outcome related type phenomena. We see clearly defined objects around us. And this happens because the probabilities of transactions are so overwhelmingly high for the kinds of energies involved, that in any second, it's that the probability is 99.9999, and it can go on nearly forever, that at any particular time you're going to have a decay. So we're at this macroscopic level. Yeah, we're going to get transactions. But interestingly, if you want to probe, there's a whole zone of the mesoscopic. So, you're dealing with things like buckyballs, which are these very large carbon molecules. They got like 60 carbon atoms in them. They have a very nice mesoscopic property where, you send them through a 2-slit apparatus, and about half the time you're going to get measurement transitions just because the thing, it transacted with one of the slits or something. So it has like a 50% probability of engaging in a measurement interaction, and you see that in the data when you work with these things.
So before I get to some more technical questions, can you outline, please, exactly what is an emission, an offer, a handshake, and you mentioned the photon was the interaction and not an actual emission or an absorption? Like, disembroil these.
Yeah. So an offer wave is a quantum state of the, again, to get a little more technical, because you did mention it earlier, we do need to distinguish between entities that count as emitters and absorbers, and these offers and confirmations. So the distinction is that entities with rest mass, such as atoms, electrons, so-called fermions, these are the charged these are systems with charge. So systems with charge that have rest mass are capable of, I mean, this is just the way the fields work. They interact in this way. So, and that's according to standard quantum field theory as well. So the interacting fields of the so-called charged fermions and the electromagnetic field give you this this potentiality to emit or absorb. But the emitters are take objects like an atom. That what's actually doing the emitting is the electron in the atom. So the only reason it can really generate something like an offer wave is because, again, the energy conservation can be fulfilled. But let's assume that's the case. So we have an excited atom. You can either count the entire atom as the emitter or just the electron within it. That's kind of the charged electron is actually doing the emitting, but you need that entire bound state to be able to do this. So let's say the electron in the excited atom is emitting. What it is emitting is an offer wave that is a quantum state that corresponds to an excitation of the electromagnetic field. But it's only the this is where we get technical. It's only the sort of the forward propagating component of that. So meanwhile, the absorber is generating what's called an adjoint field, which is a kind of advanced quantum state that it's sort of we've got kets and we've got what I call a Bragg. So they're different formal objects, but they are independently, they are forms of quantum states. So let's just say a quantum state of the electromagnetic field. We've got a so-called retarded quantum state of the electromagnetic field, which is the offer wave, and we've got the advanced quantum state of the electromagnetic field, which is the confirmation wave. So that's the offer and the confirmation that are generated under these circumstances. Let's say at time t, these were generated because it was overwhelmingly probable that it would happen at that time. So we've got this interaction between these two, and in a sense, you can think of that as the photon. In a technical level, if you had a bunch of other absorbers around, they too would be contributing an advanced offer wave corresponding to the component of the an advanced confirmation wave corresponding to the component of the offer wave that they received. So it would kind of split. The offer wave from the emitter would be broken down into many components in general. This is in general what happens. And so the photon at that level, this goes back to those stages with the first stage where we're going from a pure state to a mixed state. This is, in a sense, the mixed state for the measurement transition. It's like it's a collection of what I call incipient transactions. Now, none of these incipient transactions is actually a photon. This is where we get to the collapse stage. When you get to the collapse stage, so that one of these is actualized, then that is the actual photon that goes from the emitting excited atom to one of these absorbers. Only that at the final collapse stage is where you get this real photon that is actually, triggering outcomes. So there's a lot. Yeah, I mean, there's a lot there, and I go through that in my books, and I try to present it, at a conceptual level. But clearly, I mean, there's a lot of theoretical content going on in this process, and it's hard to kind of really do justice to that, without writing it down. But
right, and your papers will be listed on screen and in the description because the rigor is necessary, and so people can go and look that up, as well as your books will be on screen and links in the description. So just to be clear, the audience is quite technical. They comprise researchers in physics and philosophy and computer science and so on. So we speak as if we're just in the closed doors of the academy, just speaking to one
Sure.
another, and the cameras happen to be here.
Sure.
So, okay, when you say advanced waves and when you say retarded waves, are
Mhm.
people to imagine that as the same as advanced being forward in time, retarded being backward in time?
So, yeah, that's a great question because this is how John Kramer, the originator of TI, presented it initially, and this is how it kind of seems like that's the way it has to be because we usually think that everything physical goes on in space time, and space time is the mandatory background for everything physically real, and it's kind of a supposition that we all bring with us, that we've all been kind of taught. We've all just kind of absorbed that.
Speaking of absorption, yeah.
Yeah, yeah, we've all kind of been marinated in that. I initially kind of assumed that that was what was going on, but as I started to investigate the relativistic level of the formulation, I realized that you really can't consistently think of these offers and confirmations as literally little waves that are going forward in time and backward in time for a variety of reasons. I mean, um, the first is that technically these quantum states, anytime you have like a quantum state of more than one quantum system, more than one degree of freedom, um, you are dealing with a multidimensional complex Hilbert space. So these states are not entities that really have a space-time character. Their representation um, is formally mathematically much higher dimensional and complex. So they're not space-time entities. I mean, I think that people um, don't if you say, well, where do these confirmations live or where do these offers and confirmations live, then people want to go, well, they live in configuration space, but that's just a construct. And so then that gets us off into kind of instrumentalism about the theory. That gets us off into, well, they don't, whatever, they're either not physically real or if they're, that seems to create a false dilemma where you either have to say they're not physically real, they're just mathematical constructs that are useful in predicting blah blah blah, or you say no, if they're physically real, I want to be realist about the theory, so they've got to be in space time, and then what you do is you falsify their mathematical character and pretend like an object that is a Hilbert space vector propagates in space-time. That's denying its essential mathematical character. So what I've been suggesting is that we don't have to do any of that. There's a third way. The third way is to simply say that these entities are physically real, but our physical reality goes beyond 3+1 space-time. And some other physicists are starting to be open to that idea. I mean, at first it sounds crazy, and people want to put bring the guys in the white coats to take you away. When you say stuff like that, but it actually is very useful. It's very fruitful as a physical model, and in fact, the utility of it. I mean, what people would call reifying Hilbert space is to say, look, guys, these can be counted as some kind of physical possibility that is physically real, that does not have its existence in space time, but at a deeper level that I call the quantum substratum. And what you can get out of that actually is a nice theory of general relativity that includes the corrections for galactic rotation curves that are, usually attributed to dark matter. So with a colleague of mine, Andreas Schlatter, we've already worked that out. So we've worked out a theory of emergent space-time emerging from the quantum level, taken as real, taken as really involving these real entities propagating at the quantum level, and engaging in transactions in such a way that you get an emergent space-time that has symmetrical character of described by the Einstein equations. So that's all out there. That's a publication that we have, and we've been building on that. So I mean, the bottom line is No, offers and confirmations are not going backward and forward in space-time. They are processes, physically dynamic processes that are taking place at the quantum level, and they involve quantum possibilities, if you will.
So, two questions. I've noticed that the word entity is being used, and I assume carefully, and not the word particle or not the word field, like you keep saying entity. So, I want you to spell out why. And also, I want to know precisely what are the ontological commitments here? Is it that the configuration space is real, or is it that the the Hilbert space is real? Like, what? Tell me, what are you saying is real?
Um, well, I would never say configuration space is real because that's kind of an idealization of wave functions, and wave functions, which are basically amplitudes of a quantum state with respect to the position basis. At the relativistic level, you don't have a position observable. So those are kind of idealizations. But um, what I'm taking as physically real are all quantum systems. Okay, quantum systems are physically real. The field, the electromagnetic field, is physically real. So I'm taking all that as physically real. I mean, I use the term entity, maybe just kind of as a general way to reference a quantum system or a field. These can, it's kind of a catch-all term, if you will. You can, yeah. So these are real physical systems. I consider them physically real. I consider them to exist independently of anyone's observing them or knowing about them epistemologically and so on. So they're
Mm.
real. So they don't exist in space time. So what? They're real. I'm just saying the it's the ontological commitments are simply it's just I'm realist about quantum theory. So in the transactional formulation. So that means something like a hydrogen atom, which can be described by a quantum state. The state is a descriptor of a real physical object. And so I'm just being realist about it. So I'm saying the reference of quantum theory exists physically. And the fact that they don't happen to fit into space-time does not discount the fact that they exist physically. So I'm not committed to any particular metaphysical nature of what I call the quantum substratum. You could call me maybe a structural realist. I'm not
Hmm.
going to posit a substance or something like that. It's a very bare bones ontology. It's basically just the formalism in the transactional formulation, meaning that's the way I think the fields behave. These are real fields. They're really doing that. There's really an influence. There's a physical connection among physically real systems. So I take it as all physically real, and I just basically reject the idea that in order to be physically real, you must be a space-time object.
Now, I like what you said that it's a transactional formulation because it's often said transactional interpretation and abbreviated as TI, but interpretation sounds then like you're just interpreting quantum theory differently. But it's an actual,
It's different.
it's not as, yes, and it seems like there's empirical distinguishability. So I would like to ask you about that.
Well, okay. Yes, wonderful question. What I've realized as I've developed the relativistic formulation is that, yes, it is a different formulation of quantum theory. It's a subtly different theoretical model simply because the fields behave differently than is assumed in the conventional approach. As to what was the second part of your question?
Oh, I said that there must be some distinguishing factor empirically.
Yes, empirically. So the distinguishing factor is that the transactional formulation provides an account of measurement. The empirical phenomena are measurement outcomes. So the empirical distinction is simply that measurement is an anomaly for the standard approach. The standard approach is incapable of accounting for measurement. So that's the only empirical distinction. And it's one that corroborates the transactional formulation. So what we have here, this is subtle because people usually say, well, I want you to, do an experiment crucius, and show me a prediction of transaction. You say it's a different theory. So, well, show me, how does it deviate from the standard theory, and so on. That's kind of a misconception
Why?
because it's both theories are empirically equivalent at the level of probabilities. So like for the Born rule, because the transactional formulation yields the Born rule. But what people kind of don't often take into account is the issue of anomalies. So for instance, back when we had Newton's theory of gravitation, the precession of Mercury was an anomaly. The precession of the orbit of Mercury was an anomaly for Newton's theory. Newton's theory was unable to explain that. So Einstein's relativity came along and was able to and empirically predicted the precession of the orbit of Mercury. This is the same thing that's going on with the transactional formulation. Measurement, it fails to be predicted. Measurement outcomes fail to be predicted by the conventional theory. It's an anomaly. The TI formulation comes along and accounts for and predicts measurement interactions. So in that way, it is empirically distinct. This is what is usually missed, in these kinds of discussions. And the reason it gets missed is because we've all been taught, and this isn't me bad-mouthing the conventional, people who are working with the conventional theory. It's what they've been taught because the measurement problem has been around for so long that it's become habitual to become instrumentalist about the theory and say, well, it just happens, measurement happens. There's nothing wrong with the theory. It works it works for all practical purposes. It's a good instrument. And to kind of lapse into that instrumentalist stance and to decide not to hold the conventional theory's feet to the fire on this issue of measurement. If you do that, if you're a good critical thinker and you're a stubborn journalist, if you treat the conventional theory, like a politician and say, but excuse me, sir, like how do you get an outcome here? Where's your outcome? What is it in the theory that's getting you that outcome, sir? And if they don't haul you out of the, so this is what people have not been doing. So this is what, I've been to the pesky little cocker spaniel there that's biting at the heels of the conventional theory. Say, no, I'm sorry, you have not actually done that job. And the transactional formulation does that job. So that's the empirical distinction. It corrects an anomaly that exists in the conventional theory.
Does asking these journalistic questions to the politicians make you popular?
No. It doesn't, but it's fun, and it's still, I do get opportunities to engage, and they are, people are understandably reluctant. I have sympathy for that because it means going against a lot of what we've been taught, and I went through that same program. And perhaps, I perhaps have a degree of liberty to be a little more critical and stubborn and intransigent about it because I primarily work as an independent scholar. And I don't have to, I'm basically, I made the decision to follow this approach because I thought it was fruitful and it made sense to me. And I chose not to, be constrained by other concerns and to just follow this where it leads.
Talk to me about independent scholarship. It seems like there's Julian Barber, and maybe 3 other people. Why is it so rare? How are you able to do it? And what are the challenges and advantages?
Well, yeah, the advantages I just mentioned is perhaps a little more degree of independence from, what can turn into groupthink. And I don't mean that in a, it sounds disparaging, but I understand that it's a concern. And I understand the concerns people have that you take risks to buck the trend. Um, the advantage is that, I'm less constrained by those kinds of influences. Of course, it's challenging in that, financially, I'm kind of on my own. I have to be frugal. I have to work in a very limited budget. When I travel, I can only travel, to conferences where I'm invited and my expenses are covered by the hosts. I don't have any academic support for travel expenses or anything like that. So, that limits my ability to attend various things. And and sometimes if you are not, I do have an affiliation with the University of Maryland. I don't want to overlook that. And they've been very kind and very supportive, the philosophy department at the University of Maryland, to offer me that affiliation, which gives me some library resources and so on. And they've done that, out of recognition that they feel that I'm pursuing some interesting ideas. And in fact, I did happen to receive a research award in 2021 from the University of Maryland. So
Congrats.
they've been very kind in that way in the recognition. So thank you. So yeah, I mean, it just means you've got to be careful about, you got to be frugal, but you do have perhaps fewer constraints, in terms of what you investigate and how.
So we keep saying the words conventional approach to quantum mechanics, conventional. Are we referring specifically to the Dirac von Neumann axioms or something different?
When I say that, I mean the conventional view of the way fields propagate, which is kind of the basis for quantum field theory. It goes back to, this is something that perhaps isn't formalized because it's just the default assumptions about fields. The default assumptions is that fields are generated unilaterally by emitters. End of story. And it's an approach to field propagation, and that goes back to, Dirac probably formalize that to some extent, and it comes up. I mean, people who want to look at, well, what is that quantitatively, can look into the references on the issue of radiation reaction, and the issue of the puzzle in the standard approach of how an emitting system loses energy, because that's actually hard to account for in the default unilateral approach. So if people want to see, well, what is that quantitatively, they can go and see, how the traditional Dirac way of trying to deal with the loss of energy by an emitting charge is to assume that the emitted field is a retarded field only, and that is what is radiated. And when you do that, you actually have trouble saying why the field lost energy, and then you have to help yourself to this ambient free field that's just there for no reason. So those are the kinds of, publications where you're going to go and be able to see the contrast between this what I call the conventional approach to field propagation and the direct action theory.
Are there axioms of the transactional formulation, like the Kastner-Cramer axioms or something akin to that?
Nope, just the direct action theory. All you do is you say what would be happening if if nature worked with direct action fields instead of this unilaterally emitted field. And that's all you do. I don't like axiomatizing things. I never like to go, oh, okay, I'm going to postulate that. I never like to postulate stuff. So it's really simply bringing into the picture a different theory about the way fields are behaving, and examining the consequences of that. And then the formalism just falls out of it, because in the direct action theory, you naturally get these confirmation waves, these advanced states that are already part of the quantum formalism anyway when you want to construct a projection operator. A projection operator is an outer product of a so-called offer wave and a so-called confirmation wave, or a ket and a Bragg. And you get these outer products naturally from the physics of the direct action theory. They just drop right out of it. In the conventional approach, you have to help yourself to it. You have to say, okay, what am I going to represent mathematically by a state that acquires an outcome? Oh, I'm going to describe it by a projection operator. You just help yourself to that. Whereas they fall out of the physics of the direct action theory.
So in 2015, I believe, Kramer had an article. Kramer's the progenitor of this theory, for those who don't know, and I believe he called your version unnecessarily abstract or something akin to that. Why did he say that? What's the difference between his version and yours?
Yeah, I mean, I think my formulation or my version is necessarily mathematically accurate. And I think Professor Kramer very much is part of the tradition of defining the physically real in terms of is it a space-time object, and so he's kind of taken that option of this, choosing to say that these entities, these field processes, are happening in space-time because he has that metaphysical desire, requirement. So what I'm saying is just drop that and follow the mathematics of the theory in a realist way without reducing the mathematics and trying to project it down and distilling, taking stuff out of it, but leave the content intact and let that instruct you as to what nature might be about. And in fact, that's a long tradition in physics. That's in fact what Heisenberg did. When he was trying to construct these very kind of tinker toy causal mechanical models of atoms to try to get a quantum theory when he knew that the classical theory wasn't working. And it was only when he gave up on that and said, let me follow the math, let me follow the data and see what I can conclude from that. And I mean, he's got these wonderful descriptions in his writings where he says, and a beautiful structure emerged before me. When he started to kind of inadvertently stumble onto matrix mechanics.
Mm-hmm.
It was a mathematical structure that he recognized, initially at least, was kind of being handed to him by nature when he let it speak, instead of following his own metaphysical requirements about what he should impose on nature. So I think that's really, that's all I'm doing. I'm just saying, let's be realist about the theory. The objects in the theory, the quantum systems and the states that describe them have this mathematical character. Well, I'm not going to deny that mathematical character just because it makes me uncomfortable about my metaphysical, conventions. I'm going to let go of those first before I'm going to start, tampering with the theory.
In math and physics, the word space is used most often abstractly. So sure, there's up, down, left, right, and forward, backward, but there's also moduli space and so on. So, and that's not an up, down doesn't correspond to space or a subset of space-time or a foliation of space-time. So in this, grant me this usage of the word space as abstract. In your theory, in the direct action theory, in the transactional formulation, what space is it that actually exists? Is this space-time a projection of some higher dimensional space? Is it a lower dimensional, like a holographic theory, and we're being somehow moved upward to 4 dimensions? What is the space that's playing out?
Well, I take it as all real, but in different ways. So because I'm a realist about physics, I think that quantum theory is describing physically real systems. And I use the iceberg metaphor. So what I think of as, to this big iceberg, it's got this huge submerged portion, and just the very tip is peeking out, above the water. So I think that all of that submerged portion is real, but it's not the empirical component. It's not the measurement outcome component. In contrast, that's what's on the tip. So space-time is an emergent construct. It's not something we live in. It's and Einstein acknowledged that space-time is technically a structured set of what he called point coincidences. Well, it's a structured set of events, and those events are essentially the outcomes of what we call measurements. So it's an emergent construct. It's real, but it's not real in the way we thought, and but if you're strict about it, Einstein was right about the way in which space-time is real. The so-called space-time parameters, space and time, are they are parameters that help us to relate um, the, if you will, that submerged part of potentiality. It's call it potentiality
Interesting.
to the part that's observable. It helps us coordinate that. So they are parameters, and they're recognized as such in quantum field theory, that they are parameters. So it's all real. It has its different modes of reality, if you will. And I think that this calling things abstract is a very tendentious, it's a tendentious term, because it starts to make a metaphysical ruling on what you can count as real and what you can't. Like we're all used to, mathematicians love to create abstract mathematical spaces. Great. Okay. Well, usually, well, that's not real. It's some guy just created some fun thing he was playing with, and playing up with ideas. Call it abstract. Great. But when one starts to say that because the formalism or the kinds of mathematical spaces that are appearing in quantum theory are not space-time, therefore they are abstract. They have to be abstract. And it's a tendentious ruling. It's a way of passing judgment kind of preemptively and saying, I judge that to be not physically real because you're saying it's abstract. Well, it may have started out as some idea that somebody was playing with. That doesn't mean it doesn't correspond to something in the real world. So that's where the term abstract can get really kind of, it's kind of like I get a little yellow alert flag when, when abstract, because it's a metaphysical judgment. It's often used to say not real. It's used as equivalent to not real. And you can't do that. That's preemptively passing judgment on whether or not you can be realist about a given formalism and so on.
In some ways, Plato takes the approach that as you abstract, you get closer to what's most real in the realm of the forms, except he wouldn't define reality as just physical reality. What we're seeing are these imprecise adumbrations. So earlier you mentioned physical reality, and then you also just said real. So do you think that all that is real is physical?
Well, yeah, it's a good distinction to make. When I'm talking about physics and physical theories, I use physically real and real kind of interchangeably, because that's usually the domain in which I'm operating, because what my little quest, if you will, is to kind of try to offer to people a solution to the problems they purport to be concerned about in a physical theory. So I'm saying you got these problems you purport to be concerned about, like the measurement problem and other problems, and the alleged lack of compatibility between relativity and quantum theory, which we have already resolved. And so in that context, I'm offering these. And so because it's about a physical theory, that's kind of the context in which I operate. When the broader questions about Plato and perfect forms and so on, there's, if I were in a philosophy class, I would want to make a distinction between domains that we describe by what we call physics, physical theory, and domains that we don't pretend to describe by physical theory, like thought. Some people try to, but I think that's a little, a bit reaching, being materialist about that. So it depends on kind of what the domain of discourse, if you will. Yeah. I wouldn't, in this context, I wouldn't want to, say, yeah, I think Plato's perfect forms are physically real. I wouldn't do stuff like that. I wouldn't, I don't know. That's a separate question, So, yeah.
Okay, allow me to play around with this iceberg metaphor. So on the tip, are you saying the tip that's revealed, is that at least part of that space-time?
The tip is what I call space-time. The tip of the iceberg is the space-time manifold.
So you called it emergent. However, in an iceberg, it's difficult to say what's emergent. You can say it's above the surface.
That's where we need a different metaphor. So yeah, this is where all metaphors kind of have limitations. So yeah, in a real iceberg, we don't get that. It's just a way of kind of making a distinction between that which we don't directly observe and that which we do, and pointing at it's all real. It's just some of it is not accessible in the same way.
Hi, everyone. Hope you're enjoying today's episode. If you're hungry for deeper dives into physics, AI, consciousness, philosophy, along with my personal reflections, you'll find it all on my Substack. Subscribers get first access to new episodes, new posts as well, behind the scenes insights, and the chance to be a part of a thriving community of like-minded pilgrimers. By joining, you'll directly be supporting my work and helping keep these conversations at the cutting edge. So click the link on screen here, hit subscribe, and let's keep pushing the boundaries of knowledge together. Thank you and enjoy the show. Just so you know, if you're listening, it's CurtJaimungal.org, kurtjaimungal.org.
And pointing at it's all real. It's just some of it is not accessible in the same way. So the iceberg, it can only go so far. So when it comes to, kind of thinking about emergence, I switched to a metaphor of the geode. So this is kind of, the geode is this hollow gap in some rock that is gradually, there's these mineral laden fluid that's coming in to this empty space and building up these crystals. So that kind of helps to kind of visualize the way these quantum possibilities are sort of metaphorically this mineral laden fluid that's crystallizing upon the measurement, interaction into these crystals that are the structured space-time events. Oh, by the way, I'm hoping I was notified by a buddy of mine that I think Avshalom Elitzer was mentioning, his formulation and some experiments that he was kind of curious about whether TI, what TI might have to say about them, and I real quick kind of reviewed that a little bit in case you want to talk about that.
Yep. So I had a conversation with Avshalom Elitzer, and you may have seen parts of it where he mentioned the transactional interpretation directly. And so I'll link that on screen as well. In it, he references the transactional interpretation because of the time symmetry for his interpretations. He mentions the transactional interpretation also has that. And retrocausality, which Elitzer is actually a fan of, he sees TI or the transactional formulation as resonating with that. And he sees some experimental compatibility with it. So what are your comments?
Okay, well, I mean, I agree that there's certainly an affinity between the two approaches in terms of emphasizing the importance of post-selection, of what we would call measurement outcomes, and what they might have to do with the process. Of course, in TI. The absorbing systems have a lot to say about what observable you're measuring and the nature of the set of outcomes that you're going to be getting as in terms of possible outcomes for your experiment. So there's that affinity. I guess where they differ, I mean, the transactional formulation works with a specific theory of fields, the direct action theory, where you get a lot of mathematical content that describes how these fields are interacting with the emitting and absorbing systems, and that gives you a lot of this formalism, as I mentioned earlier, that is already in the standard theory. So in that sense, I feel like it's more powerful at a fundamental level, that it's more explanatory, that it generates a lot of the formalism that we're already kind of working with, but seems just kind of like we're helping ourselves to these mathematical tools. But with the transactional formulation, we get a reason for where those tools are coming from. The the time symmetric vector formulation, in a sense, I mean, formally would kind of correspond to in a way half the transactional story. It would sort of correspond to looking only at the offer wave component that reaches every absorber. And so it
Ah,
seems to me to not be it seems to me that it's only really able to work with the conventional theory and take a particular metaphysical approach to the conventional theory. But it seems to me, from what I've seen, that it's not able to specify what counts as a measurement. That it inherits this TSVF, sort of inherits that lacuna of the conventional approach to fields where you're just helping yourself to the fact that a measurement happened. And if you have to describe all the systems by these two-state vectors, then you must specify for all future times all outcomes of all measurements. So they all have to be stipulated. That seems to be just a basic requirement of the formulation since it demands description by a two-state vector. So for any quantum system, you must always specify a measurement outcome for some, arbitrary date at any time. So this to me implies a block world ontology just by what is required for it for using it. And then the dilemma sort of faced by people who want to pursue that approach is that if they want to have becoming, as I understand Professor Elitzur has talked about,
mhm.
then, I think you get into trouble. I mean, I feel like the idea of getting things to happen and getting things to emerge in a becoming dynamic way is kind of foreclosed to you because you've already said all my systems are described by two-state vectors. So you've stipulated for all systems what all future measurements will be. So there's that tension. That it's trying to I feel like again there are a lot of approaches, and this applies to other approaches that call themselves retrocausal, is they want that to be sort of a space-time retrocausation where things are literally going backward in time. So it's restricted in that sense to this literally forward in time, literally backward in time. And whenever you do that, you're really kind of working, if you think that everything's happening in space-time, then you're really kind of working with a block world picture, and then you're putting a narrative on top of that sounds dynamical, that sounds like things are going backward and forward, but you've already helped yourselves to all events. They're already there. So, I mean, I have a paper about this that I wrote back in, I think it was 2011, on this issue for certain approaches that call themselves retrocausal, but they are really kind of working in a block world ontology, and there's no real dynamics happening. So, yeah.
Is there any way to have what people think of when they think about science fiction and time travel within your framework?
Oh, not in the usual sense. I mean, you could probably talk about about it in terms of possible timelines. People sometimes like to play with possible timelines, and you can always do that, but they would be possible timelines. They would be at the level of possibility. So, I mean, it's like once you go back to the geode, once you have a crystal in the geode, there's a crystal in the geode. You can't undo the crystal. It's there, and again, another metaphor that's useful is knitting a scarf. You're going to knit
Okay.
that scarf. That scarf is emergent from possibilities, which are the yarn and maybe design. I can look at a design book and change my design at any time. I could change my yarn at any time. I could change, But once that scarf comes out, that scarf is there. you know. I mean, maybe you could, go back and put more stuff on the scarf. I don't know. I mean, people are imaginative. I don't want to foreclose, imaginative storytelling. But in the usual sense, the usual sense where people are trying to work with it in physics is they're sort of denying that, yeah, there's a scarf there,
Mhm.
and they, that's there. You admitted that's there, so you can't just go back and say that now you're going to change it. I mean, if you do that, then you're just kind of dealing with multiple space times, and then that comes out sometimes in sort of the many worlds approach. So this is a form of actualism. what I would say is that it's something that people are kind of pushed into when they don't want to just allow that possibilities are real. That perhaps physics is pointing to real possibilities.
Yes, often when people think about possibilities in the physics sense and they're thinking about interpretations, in many worlds, all of those possible worlds are actualized. So are you saying
Correct.
that this world is real, is actual, and is singular?
Well, the phenomena we see, in terms of what's actualized as a space-time event, that I take as singular. I mean, if people are free to explore the idea that these possibilities get actualized in different worlds, I would not foreclose that. It's not a necessary thing. It's not a necessary thing. The reason the many worlds, the Everettian approach comes out of the measurement problem and the inability to say what counts as a measurement. And so they're forced to just kind of look at, went back to the little train, the train with, the two engines and the two trains. Since they have no theory of fields that lets them say that an outcome happened, they just say they all happen. But that has problems with, and kind of helping yourself to the basis you want so that you get the kind of phenomena that you see. So there's some ad hoc stuff that has to go into it. And it also isn't really easily incorporated into a relativistic treatment. It's strictly the non-relativistic theory that it's working with, and the non-relativistic theory is just an approximation. So, yeah.
Bohmian mechanics has two qualities. So one is hidden variables, and the other is a preferred foliation. Do you have either of these?
No, I don't. The transactional formulation has no hidden variables. Now, interestingly, you could say it has no preferred foliation, but one of the problems with the conventional approach has been, the way to kind of say, well, what is sort of nature's preferred observable? What are things really doing in a fundamental way? And it seems as though there's an arbitrariness in kind of picking that, but there really isn't, because at the relativistic level, you get naturally preferred observables, and those are position and I mean, I said that wrong. Those are energy related, energy and momentum. So when you go to the relativistic level, it's very clear. For instance, there's no time observable period at any level of the theory. At the non-relativistic level, you can say, well, there's sort of a position observable, but it's really kind of an idealization. And that breaks down at the relativistic level. There is no position observable. And this is why even in the standard theory, position and time, the space-time labels are reduced to parameters. They are not observables. So it's very clear that at a fundamental level, nature's preferred observable is basically for momentum. And that's reflected in the TI approach. That's what you get. You get your transactions happening ultimately at a relativistic level in terms of momenta. You can have directional momenta in the sense that you have a variety of absorbers, and they're each going to receive a different directional component of momentum, and that's more of a relational thing. So it has to do with the relations among these quantum systems. So you don't need to talk about space and time as being real, but they are parameters of the map, if you will. They're parameters of the map that help us coordinate these relationships. So this is kind of a relational view of space-time. It's not saying that space-time doesn't exist, but again, as Einstein noted, what the space-time manifold really is an invariant set of events, period. It's not about X or T. It's a collection of invariant events. And we use X and T to coordinate our observations among those events.
Now, earlier we talked about electrodynamics, and you grazed on gravity and somewhat grazed on the weak interaction as well with the Schrodinger's cat, although it was unclear to me the connection between the transactional formulation and the weak interaction. So what I'd like to know is, does TI have anything to say about weak or strong?
Well, the transactional process that leads to the emergence of space-time events occurs only through the electromagnetic field. The other forces are certainly in play at a fundamental level. They govern the unitary interactions, the kinds of scattering, interactions and so on. Now, the weak decay, the weak forces involved in decays, and of course, the Schrodinger's cat, you can illustrate that with just a decay in terms of an excited atom emitting a photon, if you want, right? So it doesn't have to be it doesn't have to be the weak force. But the weak
Exactly.
force is certainly really in there in terms of these unitary interactions that transform, that kind of govern these kinds of transformations among types of particles and so on. And that's very much part of the transactional picture. So in other words, the transactional formulation very much accommodates all those fields. The thing that it treats distinctly is the electromagnetic field, because that's a massless gauge field. So you require a massless gauge field to get you the emergence of space-time. So these other ones have mass, and so they are unstable in a sense, and they act only really kind of locally at the quantum, at the level of possibilities. And not locally, but they act at the level of possibility, if you will. So these are force-based interactions, the strong and the weak force that are going on, metaphorically speaking, in the submerged portion of the iceberg. But they're very, TI doesn't deny any of that. It's very much part of the same physics.
Another massless gauge field is gravity, or at least under some interpretations of quantum gravity, you have the graviton. So does TI make any claims about that?
So we deny that gravity is a quantum field. So what we get, we basically say the mistake in, that the problem, that what's so problematic about trying to reconcile the quantum level with the relativistic level is trying to characterize gravity as a quantum field. So gravity, we say, is not a quantum field. It's a the field is the metrical structure of the emergent space-time. End of story. And that's what Einstein said. He said that that's what the field is. It's the metrical structure of space-time. So it's a property of those sets of events. And so, people who want the detailed story of that, they want to see see the actual math, see the actual theory. We do have an actual theory that derives the Einstein equations from that picture.
So then, is the transactional formulation a theory of everything? A contender for a toe?
Well, I guess I never like to claim that. I guess you could say that it's a theory of the quantum level and the space-time relativistic level. I guess I'm not clear in myself that physics can explain, everything about reality, including people's thoughts, motivations, and intentionalities, consciousness. And so, from that standpoint, I would never, I would be a little more modest about the reach of physics. But within topics that are considered physical questions, yeah, you could say that, because it's definitely providing an account of the interaction of the quantum level with the space-time level, with the the relativistic level, and it's quite straightforward.
Yes, well, in physics, the term theory of everything is just for a framework that encompasses both gravity and the standard model.
Sure. Well, yeah. The TI, the transactional formalism, again, is simply contained in applying the direct action theory of fields to the kinds of physics we're already working with, and admitting that saying fields propagate unilaterally and retarded fields only is wrong, replacing that with the direct action theory for the electromagnetic field. That's all it is. And we're just showing how fruitful that is, what you get out of it. So, I mean, the transactional formulation does not purport to explain the origins of quantum chromodynamics or anything like that. But where appropriate, the claim is that nature is behaving according to the direct action theory of fields. And let's see what that gets us. And we are already showing, how much we get from that.
In many physical theories, or in virtually all physical theories, there are parts that don't change, and then there are contingent parts. So, for instance, the force equals mass times acceleration for Newtonian mechanics, it doesn't change, but initial conditions are contingent. So, what are the parts of your theory that are contingent, and what are more constitutive?
Well, I mean, it's really the same, I mean, it's still the case. And, the only thing different about this theory is the way that the fields operate, the way that the electromagnetic field behaves. So we're still going to have, Newton's laws as a suitable non-relativistic approximation. We're still going to put in initial conditions. Um, and in a sense, yeah, so then none of that's really going to change. But I think overall, in the big picture, it's a more satisfying account because you help yourself to initial conditions that, at least for the for quantum situation in the conventional theory, are just stipulated. Like you can't say why you got a measurement result. So in the transactional formulation, you can at least say, well, I there was a measurement interaction, and I can explain why that happened. And then there was perhaps a collapse to a result, but I can say why there was an outcome available to me. So, yeah, I mean, fundamentally, it's not going to change those kinds of features of theories.
Does it have anything to say about Bell's inequalities or the Kochen-Specker theorem?
Well, those are uh, basic theorems that point to the non-locality of quantum theory. And that is certainly still the case in the transactional formulation. I mean, unlike some interpretations, the transactional formulation does not, at least as I've elaborated it, it's not trying to preserve locality. This, I think, is very much, you know, trying to cling to some metaphysical ground rules that are not really serving us well. The quantum world is non-local in a sense that's what the violations of Bell's inequality and so on are showing us. And maybe that's uncomfortable, but once again, if you allow the idea that nature does have this level of possibility, then it makes sense that you're going to be observing things that look non-local to you, that there are interactions that can go on that seem to defy your expectation that everything's happening in a space-time container. So that, I would say, that's very much those are authentic implications of the formalism of quantum theory in the sense that there are non-local influences going on.
Okay, so two quick questions about that before Kochen-Specker. So you said it looks non-local to you. So does that mean that underneath the iceberg, there's some version of locality, maybe it's not called locality, that is preserved, and then when it gets emergent upward or in the geode picture, it looks like it's violating locality?
Well, I mean, in the usual sense, it's in the sense that there are influences that seem to propagate at speeds that are, seem to exceed the speed of light. They are technically non-local, but where we can gain some insight into those uh, influences not being something that we should forbid, it's helpful to look at the flatland metaphor. The flatland Edwin Abbott story where there are flat shapes in a plane, and they think that's the entire reality. But if it isn't, then you can have these, the sphere hovering and coming and doing these weird things that from the standpoint of the flatland creatures look non-local and crazy and know this can't be happening according to the rules of my world, which tells me I can only stay on this plane and only can do this, right? But those rules don't apply to to an entity that has more degrees of freedom and more higher space to work with. And that's the sense in which I think these non-local interactions are occurring. Strictly speaking, by the rules of getting from here to there on flatland, they're violating that. But it doesn't mean that they can't really be happening and that we shouldn't, it means that, okay, there's just a larger aspect to reality in which more kinds of influences are possible. And again, these do not violate relativity because the influences that are happening are not sending light signals. So it's conforming to relativity, but it's violating our sense of propriety concerning what we think should happen in flatland. And so what I'm saying is let's let go of that, that restrictive sense of what's okay and what isn't okay in terms of what's physically happening. So yeah, non-locality from the standpoint of influences being able to be communicated that don't depend on light signals. Yeah, that does happen in the direct action theory, and it's okay. It doesn't, it's not something nature's not allowed to do just because we don't like it.
So is the non-locality just a correlation, or is there causation to it?
Well, this depends what you mean by causation. For instance, the scattering, interactions that you referenced earlier, those are brought about in terms of non-local connections among the electrons. So that time-symmetric propagator that connects those electrons that are scattering, it's clearly doing something. It's causal in the sense that it's doing something, but it's pre-measurement. It's not something that is connected to a space-time event. It's part of the sort of behind-the-scenes dynamics that's building up to make certain events more probable than others. So it's definitely doing something physically efficacious, but it still respects relativity in that, it's not something where you're using a controllable light signal and sending a signal from A to B and so on. It's happening at a subtler level.
You don't violate the no signaling theorem.
That's correct. Not at all.
I see.
Yeah.
Okay, so let's get to Koch and Specker. What is your account of it? And also, can you please tell the audience what that theorem is?
Well, the Koch and Specker theorem is basically a theorem that shows that what kinds of phenomena you can come up with are contextual. That you cannot say for all observables I can assign a yes or no answer. For all cases. And this has to do with the fact that Heisenberg's uncertainty principle and the fact that observables don't commute. So it's a consequence of that, the non-commutativity of these observables that only, that for two observables that don't commute, like position and momentum at the non-relativistic level, you can't just say, I can assign a determinate momentum property for the system for all, cases and also a determinate position, that it's really this position and not all of these others. So you can't just have a space where you clearly lay out determinate yes or no whether this system has this momentum and that position. You can't make a collection of these outcomes for mutually incompatible observables in this way. And this is perfectly fine. This is a feature that one would expect at the level of possibility. Because again, possibilities are not determinate outcomes. And while you have it's a feature of these possibilities that when a system can be said to, has been, say, set up or prepared in some determinate state of momentum, it really does not have a determinate position. And this is simply because in the transactional approach, we would say, well, it hasn't transacted. It's if it hasn't transacted, if it's clearly got a momentum, it hasn't engaged in a determinate kind of measurement interaction that would create an event. And we always end up sort of specifying events with space-time parameters, but again, these are all frame dependent. So it's just a fact. It's the way these possibilities work that by definition, if you have a determinate momentum, you are behind the scenes. You have not engaged in a particular transaction that would actualize a space-time event. So it's kind of a natural outcome. There's no reason to expect that a system, quantum system that is existing at this level of possibility should be a space-time object, right? The expectation that we want things to be non-contextual, or the surprising fact about the surprising effect on us of the Koch-Specker theorem is that it contradicts our desire that everything seem to be having a determinate momentum and position, because that's kind of what it looks like at the macroscopic level. But in fact, at the quantum level, that's not the case.
So speaking about these possibilities, and they have probabilities associated with them, do you have a philosophy as to what these probabilities mean? Like, there are different approaches: frequentist, propensity, Bayesian. What are these probabilities exactly?
I mean, I would call these propensities, the kinds of probabilities that we get from the Born rule that comes out of the transactional formulation. I think the most natural way to interpret them is as propensities for actualization. They're weights, if you will. So you can kind of see it as a weighted symmetry breaking, that there has to be something indeterministic that's happening to actualize one outcome over others, but that's weighted, so that it's not always equal probabilities.
And the Born rule, is that able to be derived from something more fundamental, or is it assumed?
Oh, no, exactly. It is derived. It comes right out of the physics of the direct action theory. And so that's what I've shown in papers and in my books. And the most recent one is the Cambridge second edition that came out in 2022, called The Transactional Interpretation of Quantum Mechanics. It's subtitled A Relativistic Treatment. So that version has, updates on the relativistic development, but it also does go through where you get the Born rule from the transactional picture. So that also, I think, is one of the selling points of the transactional formulation, is that the Born rule is derived from it, rather than just, Max Born. I mean, it's kind of funny how he, in a paper in 1930, he originally talked about wave functions as probabilistic descriptions, but he realized that the amplitude, that's just an amplitude. It doesn't behave like a probability. It's complex and so on. And he said, well, to get the right mathematical behavior, you need to square this thing. So that's how we got the Born rule. It was totally ad hoc. I mean, obviously a smart idea, but it was an ad hoc, look, the amplitude isn't giving me the right kind of number, so I better square it, and then I'll get the right kind of number. So we can do better than that in the transactional formulation.
To you, what makes something ad hoc? Because some people may hear backward traveling waves, even though you have some issues with that, or they'll hear handshakes and they may see that as, oh, that's ad hoc. So what makes something ad hoc?
Where there's no theoretical basis for it. You have to help yourself to it in order to get things to come out according to the empirical observations. A prime example is the Ptolemaic geocentric system of the solar system, the model of the solar system. So the epicycles, those are ad hoc, right? I mean, he had stuff that was, okay, everything's going around the Earth. Oh, I've got this stuff. Why is that planet going backwards? It looked like it was going backwards. Let's see, how can I, it's a Band-Aid. How can I patch up my theory? I mean, it's basically saying, this is kind of an anomaly for my theory's having trouble explaining this. I better come up with a Band-Aid to patch that up. That's kind of what it is. I mean, and some people you have to be careful because, some people might say, well, backward stuff is ad hoc. Well, if they don't know what the theory is, they don't have any basis for judging whether something is ad hoc or not. So you have to know what you're working with. What is the theoretical model? What are the phenomena? Does the theoretical model predict these phenomena? If so, there's nothing ad hoc about the theoretical model. It becomes ad hoc when the theoretical model is failing. It has a gap or is saying something different than what you see, and you want to keep your model. You start band-aiding, you start patching it up. Those are ad hoc things. Or when you'd have no model.
Mm-hmm.
And you just say, and that's kind of what the Born rule was. It works, but there was no theory behind it.
Ruth, what was the most difficult decision you made during your career?
Oh, probably to switch from physics to philosophy. I started out. I got into physics because I thought electromagnetism was magic. I was just enchanted by it. I'm enchanted by light, and the fact that back when I was a child, that you could have a prism and see white light being broken up into colors, and just I was enchanted. So I was enchanted by physics. It's also in my family. I have a lot of family members who are physicists, and when I went into physics at the graduate level at the University of Maryland and came across the EPR, the Einstein-Podolsky-Rosen, thought experiment, and so on, and the non-locality, that's when I became really fascinated with these puzzles, with the paradoxes of quantum theory. And it was at that point, after I got my master's, that I decided I really wanted to pursue that kind of examination. And I learned that they were doing that in the philosophy department with Jeffrey Boob, Alan Stairs, and some people there. So that was a tough decision, but I'm really glad that I made that decision.
Now, I guess a meta question. Was that decision yours to make under your framework? Is there free will?
Oh, yes. Yeah. I mean, I think, and I've argued, I have a couple of papers on this, and I address it in my books that free will. We have constrained will. We're not completely free, but there are live choices. I believe there are live choices, and I've also argued that there is no sense in which physics rules that out. I mean, it's very common for physicists to issue these edicts, that say physics says we do not have free will, and that's very much incorrect. It's those kinds of judgments are made based on certain interpretations of the physics and certain unnecessary kinds of metaphysical presuppositions that people bring into it that they may not don't be aware they have. So yeah, the physics definitely allows room for there to be real life choices. And in fact, I've argued that that's quantum theory actually suggests that's what's happening in nature.
Okay, so I assume what you're referring to is libertarian free will. Am I correct?
Yeah, I mean, I don't necessarily go along with all the traditions of that approach, but I think there's physics leaves room for there to be unpredetermined choices on the part of agents. Now, what counts as an agent is a huge question. That physics may or may not have anything to say about, but physical theory definitely allows for, even Heisenberg talked about photons making choices when deciding whether to go through a polarizer or not. So there's room in physics for that, for live choices.
If the transactional formulation doesn't care or doesn't make claims about observers, and observers are tied to consciousness, and consciousness is tied to free will, which feel free to dispel any of those claims that I just made, then I find it difficult to see how TI can have something to say about free will in a libertarian sense, because it sounds to me like it would just be probabilistic. And if it's just probabilistic, I don't see where the choice is if it's already given to you by the Born rule. Unless it's non-deterministic where the probability distribution is not known.
No, the probability distribution is given by the Born rule. I mean, I would never say that the transactional formulation has anything to say about free will. That this is just me talking,
I see. Okay.
But kind of given, like, suppose I think that nature does behave this way. I happen to think it does. I mean, if somebody's found something terribly wrong with this, I would, I'd rethink that, I'd re-examine that. But, if nature really does work, in a way, according to this direct action theory of fields, that in itself is a different subject from free will. All it does is say physics won't forbid it. That's the most that it can say. If this physical theory is genuinely indeterministic, then it leaves room for there to be some theory of free will. It doesn't tell you there is or isn't. It just leaves room for it. Which is opposite from, many physicists will say physics tells you don't have free will. And I really don't think that's a fair thing to say, right? So it's delimited in that way. I mean, me just speculating, I obviously consciousness, I mean, personally in my own views, I do think that that you're going to have trouble accounting for consciousness if you're materialistic, and if you assume the Cartesian dualism type thing, or if you assume that physical matter is as Descartes envisioned it, which means it's dead. It's by definition non-sentient. Then you've got the hard problem, and you're not going to get consciousness out of that. So that's my view, and I think that consciousness is something that's much more fundamental than any physical theory.
Interesting. So you think what lies underneath the iceberg of the iceberg is consciousness? Or perhaps it's the ocean?
Well, yeah, I really think so. I mean, just in a purely logical sense, folks, if you're going to say that the building blocks of nature are dead and non-sentient, then forget it. You're not getting consciousness out of that. End of story. So I'm just to be logically consistent with myself, I am forced into a posture of saying that consciousness must be in there at the basis of everything. It's just on a logical basis. I mean, by the hard problem. There's only a hard problem. There's only a hard problem if you assume that everything's dead. So I mean, physics doesn't need to postulate that matter is dead. I mean, why do that? There's no reason to. It's unnecessary. It's just a metaphysical choice that's optional. In my opinion. Seems like it, like I can say, well, there's matter that described physics deals with something we call matter. I'm not going to add to that has to be dead. Why would I do that? That's stupid. Why do that? I mean, that's just an assumption. It's dead. Why do we have to assume physics describes dead stuff? You don't have to. There's no reason. Or non-sentient. I'm going to define matter as non-sentient. Why? Nobody put a gun to your head. You didn't have to do that. You can, I mean, to me, it's kind of hubristic. Just say, okay, you don't know what life is. You don't know what consciousness is. So that doesn't mean you have to forbid it from being part of your theory. Just say your theory doesn't have anything to say about it. Maybe later it will, so. That's my position, is don't foreclose possibilities if you don't have to.
Would you say that rivers or a rock or snow or H2O or carbon dioxide have experiential elements to them, or that they're conscious?
I don't know. I mean, I can't assert that. But like Heisenberg himself said that the photon is making a choice whether to go through the polarizer. So maybe they do. I mean, again, that's a question of at what level could you say something begins to be like self-conscious or begins to be deliberative? And, I don't know, who knows that I don't purport to have those answers. But certainly the indigenous traditions thought so, and people might say, well, they weren't scientific. Well, maybe they were, but in a different way. So, I mean, people have traditions that kind of take that for granted, and of course, those kinds of traditions are usually dismissed by the Western approach. But maybe we need to be a little more open-minded. I mean, we still have to be physically rigorous, And I started out on this exploration being very much, like a Sam Harris person who deprecates anyone who talks along these lines, who talks about, things that are not strictly materialistic and involving Cartesian dead matter. So I've been there.
So what changed you?
That it's logically inconsistent. You can't get, I mean, that's the main thing. You can't get consciousness if you preclude it from the outset on a logical basis. And, and also I happen to be, I'm a philosopher, and I happen to be interested in various spiritual traditions. And I'm a yoga teacher, so I know something about Indian philosophy, and I've come to respect other traditions and other ways of knowing, as having some insight and having, approaches to knowledge that maybe are not within the kind of Western usual scientific paradigm, and along with its sort of constraints. But I've come to respect the some of the wisdom of those traditions. So while I would never try to mix them, I think there are different ways of knowing, and I try to be scientifically rigorous. And when I'm working with physics, I don't postulate stuff that I don't think is warranted. And I try to be logically consistent and try to see where the theory leads me. But, when it comes to things like consciousness and life, physics needs to be a little bit more modest, and needs to understand what's within its domain of accountability and what isn't, what it can explain and what it can't. And that it shouldn't, that scientific inquiry doesn't need to be constrained and circumscribed by optional metaphysical premises that maybe were useful as kind of training wheels. I think of them as kind of training wheels, that sort of mechanistic approach that led to Newtonian mechanics and so on. But at some point, maybe you need to recognize what's on your bike, what's your bike that's really going to get you places, and what are training wheels that are holding you back. And I think that's where we are now with the mechanistic way of looking at things.
Do you think that we're being held back from further physical inquiry? Is that what this the tricycle being too slow metaphor is talking about? Or is it something like spiritual advancement that is holding us back from?
Well, I mean, really, in terms of physics, we're being held back, I think, from progress in solving a lot of these problems, by physicists not really wanting to consider this direct action picture, this transactional formulation, because it violates their training wheels, because it violates this kind of mechanical, always forward directed space-time is the entire domain of what's physically real. Those kinds of presuppositions, it challenges those. And I think of those as the training wheels in the field of physics. And I mean, again, as our publications show, we already have presented solutions to problems that you'll see people, I see papers constantly come out and say, measurement remains enigmatic in quantum theory. Nobody knows what a measurement is. And I'm like, well, I've been telling you what it is since 2012, and Kramer did 1986. So this is that it's bouncing off, that the answers are there, and they're bouncing off because the conventional approach is still, I want my training wheels. Because the price for accepting these kinds of solutions is you got to let go of your training wheels, and you have to let go of your demand for what you call locality, your demand for determinism and mechanical explanations. And those are the training wheels. If you let go of those, you have answers to these problems. We've got the publications. We've got the answer to reconciling the quantum level with the relativistic level. It's out there. And so when people say, we've still got this problem, this unsolved problem of how to reconcile quantum theory with relativity. Well, read the physics communications paper that we've put out in 2024. The answer's out there. So it's a question of seeing it, seeing that there's an answer, and maybe you don't want to see it because you don't want to lose your training wheels.
Do you believe that the primary reason for physicists not taking, say, the transactional formulation seriously is because of their recalcitrance or their ignorance, and that if only they would read it and not be so blinded by their preconceived notions, that they would be accepting of it? Or do you see that actually there are some substantive issues or challenges that remain with it? Because even when I speak to people like Penrose or to Avshalom or almost anyone who has their own formulation of quantum mechanics, they'll say something similar. Like Penrose may say, well, we have this conception that there's computability at the forefront of the brain. If only we would get rid of that, and we would understand that consciousness is what collapses or what is produced by the collapse of the wave function, then if only physicists would take that seriously. Or Avshalom with, if only physicists would see that there is something actually unique about the now and it's not a block time, et cetera, et cetera. So almost each person will say, if only physicists would so-and-so remove their prejudice. And so I'm just curious what you think.
Yeah. Well, I do think that, I wouldn't call it ignorance, but I mean, it took the Copernicus heliocentric model 200 years to be accepted. We have to be patient, I think, for progress. Is that because again, there's a certain tradition, and traditions are valuable. They provide structure. They do yield progress, but then they can become constraining. And it's a slow process for people, as a community, to start to get a little distance from metaphysical conditions and see what they are first. What are my metaphysical assumptions that I'm bringing to this? Do I really need these? Are these things that are maybe not necessary? And to have the option of letting go of it, you first have to see that it's not necessary. So, it's a gradual process. For those other, obviously those are alternative approaches, but their interpretations. Penrose has a certain kind of a collapse formulation. His approach is actually empirically distinguishable from the conventional theory. So he has a different mechanism for collapse. But anyone, again, it's true that anyone who's challenging a prevailing, conventional approach has to be patient, because it is a process of people choosing to become aware of, what am I bringing to this? Do I need to bring this in? Do I need this expectation to be an imposition on what the theory could be? Or maybe my expectation is optional, and maybe nature has a different way of behaving. So it's a gradual process, and you have to be patient.
What are the parts of TI that you're working on? Like, what are the holes that currently exist? And sure, they can be patched up, but where do you see its shortcomings?
Well, currently, I'm not finding any holes in the sense that it's failing to account for X. I'm not finding holes. What it remains to be done is to elaborate, the consequences of the predictions of the model. And that's very much, I'm getting some help from some colleagues of mine, Andreas Schlatter, who's working on the general relativity aspects, and a new collaborator whose name I won't mention yet, because he's maybe not fully on working on it yet, but I've gotten some very promising communications from someone who's working on the quantum field theory end. So it's mainly elaborating the consequences, and I'm not seeing any holes in the sense of it's falling short of accounting for X, and I haven't gotten that. I haven't gotten any such criticisms. When I get criticisms, what I always find is that they're working with like an earlier version of the model that they haven't updated themselves, that the critics are not updated to the latest work, and they haven't done their homework, so to speak. So I have not gotten any criticism from someone who's actually read the material saying, well, you can't explain X. I haven't gotten anything like that.
Going back to holes, and not with the TI, but with physicalism, the response from someone like a Neil deGrasse Tyson to saying that, well, consciousness may be at the basis and physics doesn't explain everything. He may say something like, okay, well, look, if we take a look at psychology, then that becomes neurology, which becomes chemistry, or biochemistry, which becomes chemistry, which becomes physics. at what point of this conversion is there a failure that you can point at? If you can find a point at which one of the layers doesn't emerge from the previous one, well, you'd win a Nobel Prize. Like, show me where the laws of physics fail. So what do you say to that?
Well, the laws of physics fail right away, again, on the hard problem, if Neil deGrasse Tyson assumes that matter is non-sentient. If, I don't know. I mean, if, in other words, if you want to be what they call materialist.
Yeah, he claimed to be a materialist when I was
Right.
speaking
Well, he's
with him.
already failed on the hard problem then.
Okay.
And this, you can see that in his desire to reduce internal conscious experience to neurons. Neurons presumed to be made of dead, non-sentient matter. That is an optional metaphysical choice that in his mind he sees as mandatory, and he wants to impose on everyone else and pass negative judgment on them if they don't do what he does. So much as I admire, his accomplishments, that's a form of hubris in being reductionist in that way, and it's just kind of a casual, naive approach to these really nuanced, important, subtle problems where he hasn't even figured out that he's already failed on the hard problem. So this is what you often get with materialist, physicalist kind of dabbling, if you pardon the expression, as being a little pejorative, in these issues where they don't even notice where they're contradicting themselves. And it's kind of embarrassing.
Now, if you had to give a single killer app, like a single great feature of the transactional approach that there are researchers who are watching, just so you know, there are professors of physics and computer science and mathematics and so on who watch, and then there are also young researchers who want to get into the field. They're listening and they want to know, okay, what would it be that if I was to play them the next 5 minutes or the next 3 minutes, what would it be? What would be the killer app that would make your approach superior to the alternatives?
Well, a killer app, this again gets to the desire to have a formulation, have a new product, a new spin-off that the old paradigm did not predict. Something new. We want something new. Like my nephew Drew, who does amazing, virtual reality apps, and he's brilliant. No, I'm sorry, folks. All this gets you is a solution to the measurement problem. It gets you the reconciliation of quantum theory with general relativity. It gets you, a quantum theory of gravity from a direction that maybe you weren't expecting and maybe you don't even want, but it's the solution to many purported problems. And so that's the killer app that it gets you. That we need to remember that the conventional physics that people are working with fails to tell you why you ever got a measurement outcome. It fails to do that. And so that's what this will get you. It gets you consistency. It gets you a physically consistent theory that doesn't founder on such, thought experiments as the Wigner's friend experiment, the Froschiger-Renner inconsistencies. It gets you theoretical consistency, and it gets you reconciliation among these different levels of the theory. So I think that's quite a lot. Maybe not a killer app, but it solves a lot of problems that people say they're concerned about.
So in other words, you're saying, forget killer app. I'm going to give you the whole phone for which all your other apps are based.
I think so. And it's like, well, it's like, well, we don't want that phone because you're saying that space-time is not the delimiter of everything real. And we can't, that bothers us. I'm saying, well, I'm sure the heliocentric theory really bothered the church. It really bothered a lot of people who had been brought up to believe that. And I understand that. And I am sympathetic to it. But, this is a solution, and people who want solutions and are willing to think about what training wheels they might be working with, that they might not recognize as what they thought were important theoretical, square one ground rules, and actually unnecessary constraints that you don't need to be working with.
How can we generalize, or how can you generalize the transactional approach to address open quantum systems where density operators evolve according to Lindblad type master equations?
Oh, absolutely. I mean, it's completely general. So, I mean, any kind of it's not at all restricted to closed systems. I mean, it's a completely general approach. So, um, Lindblad equations and master equations, diffusion type equations. If I understand correctly, yeah. In fact, I've written about how that's in my book, my CUP 2022 book, about how we get, master equations make a lot more sense in the transactional picture. Because once again, within thermodynamics, when you're dealing with a master equation that's telling you about equilibrium conditions and approach to equilibrium, you actually have to do a little fudging and help yourself to a probabilistic description when the conventional quantum theory will not let you do that. Or it won't give you any reason to do it. So that's where there's we'll just wave our hands and we'll say, well, we think we have probabilities now, and now we will use our master equations. So in the transactional approach, you don't have to wave your hands over that. You clearly have real physics that tells you why you get master equations.
What is the Afshar experiment?
Oh, okay. So the Afshar experiment was a clever way of looking like it was measuring two non-commuting observables in the same experiment, and thereby, kind of violating the uncertainty principle, or at least the Bohr's notion of complementarity. And it wasn't doing that at all. Again, it's fine to do experiments, and it was a lovely experiment. Where we get into trouble is talking about the implications of experimental results and the bearing of the experiment. And here's where I think Afshar went a little too far in his interpretation. And what I've written about, and I can give that reference if people want, is that we had a measurement of the, formally equivalent to preparing a particle, say, up along X, measuring it again and saying, yeah, it's up along X, and then measuring it along Z and getting some answer. That's all it was. So there was nothing, it looks more impressive when you do it in the kind of, position basis and so on. But all it is was, a preparation, a confirmation of the prepared state, and then a measurement of a non-commuting observable. And that's all it was. So it's fine to do experiments, and where you get into trouble is making claims about what the experiment showed you when those claims aren't necessarily supported by the experiment itself.
Now, I have one last question from the creator of Formscapes, which is a YouTube channel, and I'll put the link on screen and in the description. He says, I assume the topic of reverse causation is going to come up, so I'd like to suggest a question. How does Ruth feel about the possibility of interpreting these phenomena as indicating that separate entities are already interconnected by default, rather than interpreting them as indicative of reverse causation?
Well, yeah, I mean, I think at a subtle level, that's a good way to look at it, that these apparently separate entities, I mean, certainly if they're charged particles, they are always connected in the direct action picture by the time symmetric propagator, by so-called virtual photons. And so they are always connected, and in that sense are never truly separate. So I personally think, I mean, I'm not sure that what the questioner has fully in mind, but certainly at a basic level, at a superficial level, I prefer to think of the phenomena that we see as coming out of this connectedness that exists already at the level of possibility, that is physically real, and that the emergent phenomena are coming out of that, rather than saying that things are literally going backward in time, because I just don't think the physics gives you that.
What advice do you have to the younger generation? And I should say that when I say younger generation, there are also people who are in their 50s, in their 60s and 70s. And actually, there's someone who's in their 80s who's just getting their PhD emailing me.
Wonderful.
So I just mean people who are not done with their research.
Wonderful. Well, I would just say, do a lot of introspection. You know, try to when you're looking at theories and when you're looking at presentations of ideas, try to be a critical thinker and to kind of examine for yourself what are my expectations of nature. Are Am I possibly imposing something on nature that nature might not be doing? And I always tell myself nature is the final arbiter. I have to be obedient. I have to think of myself as a student of nature rather than, imposing my preferred, metaphysical view on nature. And really, that's a lesson that we get from Heisenberg, going back to when he came up with quantum theory. That is what he did. He really kind of what I kind of think of as Zen beginner's mind. It's good advice. It's like go back to be teachable. Let the phenomena be your data and let possible theories just be ways to create relationships among the data that might turn out to work for you, to be corroborated. And if they are corroborated, to me, that suggests that they have some physical relevance. And again, it's because that's kind of a realist approach. But it's let the data and let nature teach you what it might be doing rather than take things like, well, we must impose causality on our theory. We must impose symmetry on our theory, which is an approach that has become traditional in physics. And those I call the training wheels. Maybe we need them, maybe they're not, but that's the thing to look for is while you're learning, be a student of nature and just be alert to not put constraints on nature that nature doesn't really have.
Thank you so much. I appreciate the time that you've spent with me. It's now, 2 hours, 2.5.
Always a pleasure.
Wonderful.
Thank you for the opportunity. I love the chat.
And I just want to say that I respect people who get their PhDs when they're older, because one of the worst things you can do is concretize your worldview, your Weltanschauung, as I say, when you're in your 20s, which is what most people do. If you ask almost any one of the famous physicists, what is it that you believe? And they're 60, they're 70 now, and you ask them that when they were in their late 20s, it's approximately the same in terms of ontology.
Yeah, it's good to try to be flexible and be a lifelong learner. And often that is hard when you get your PhD very young. I got mine, I guess, when I was about 36 or something. So I had done a lot of different things, and
you get to explore before diving.
Absolutely, absolutely. And even when you do that, you always need to be wary of things that are passed on as, yes, this is the way it's done. And go, okay, well, maybe the reason you still have problems is because that's the way it's being done. Rather than just be obedient, and hey, you have to be disobedient sometimes. I mean, Einstein was in a patent office, right? So, sometimes you just have to go off the beaten path to find the solutions and to really find understanding.
Ruth, it's been a pleasure. Thank you so much.
Well, thank you so much for the opportunity. Really, really enjoyed it. Thank you for a great question.
I also wanted to take time to thank people who have joined as a YouTube member. Someone who's been here for 13 months, over a year, is Mike Clark. Thank you. Thank you to Dima. Thank you to Alan. Thank you to Neil. Thank you to Charles Matthew. Thank you to Ike. Thank you to A_MB. Thank you to Eric Weinstein. You've been a member for 6 months. Thank you. Thank you to Dr. Y. You've been here for 5 months. Thank you to Yuri. Thank you, Eric Green. Thank you, Mike. Thank you, Unreal. Thank you, Nicholas. You've been here for 4 months. Thank you, Carlo Ravelli. You've been here for 3 months. Thank you to David. Thank you to William. Thank you to Richard, Ether Topo, to Cosmic Felon, great name. Thank you to Emmy Johnson. Thank you to Peter Kellner for 2 months. Emmanuel, Borko, Ioannis. Thank you, Nut. Thank you, Human Intelligence. Thank you, Mark. Thank you, Doc. Thank you, Adam. Thank you, Metmit. You've been here for 1 month. Thank you, Argentine, Beth, Emery, Casey, Sigmund Freud. Thank you, Terry Bollinger. I appreciate you. I know you comment all the time. It says that you've rejoined and you've been here for a total of 1 month now. Thank you. Thank you, Notchum. Thank you, Syria. Thank you, Tamer. Thank you, Train. Thank you, Dan, who has just joined along with Train and Tamer. Thank you so much. The way that you can join to be a YouTube member is on screen, and the link is in the description. New update. Started a Substack. Writings on there are currently about language and ill-defined concepts, as well as some other mathematical details. Much more being written there. This is content that isn't anywhere else. It's not on Theories of Everything. It's not on Patreon. Also, full transcripts will be placed there at some point in the future. Several people ask me, "Hey Kurt, you've spoken to so many people in the fields of theoretical physics, philosophy, and consciousness. What are your thoughts?" While I remain impartial in interviews, this Substack is a way to peer into my present deliberations on these topics. Also, thank you to our partner, The Economist. Firstly, thank you for watching. Thank you for listening. If you haven't subscribed or clicked that like button, now is the time to do so. Why? Because each subscribe, each like helps YouTube push this content to more people like yourself. Plus, it helps out Kurt directly, aka me. I also found out last year that external links count plenty toward the algorithm, which means that whenever you share on Twitter, say on Facebook or even on Reddit, etc., it shows YouTube, hey, people are talking about this content outside of YouTube, which in turn greatly aids the distribution on YouTube. Thirdly, there's a remarkably active Discord and subreddit for Theories of Everything, where people explicate TOEs, they disagree respectfully about theories, and build as a community our own TOE. Links to both are in the description. Fourthly, you should know this podcast is on iTunes, it's on Spotify, it's on all of the audio platforms. All you have to do is type in Theories of Everything and you'll find it. Personally, I gain from rewatching lectures and podcasts. I also read in the comments that, hey, TOE listeners also gain from replaying. So how about instead you re-listen on those platforms like iTunes, Spotify, Google Podcasts, whichever podcast catcher you use. And finally, if you'd like to support more conversations like this, more content like this, then do consider visiting patreon.com/KurtJMungle and donating with whatever you like. There's also PayPal, there's also crypto, there's also just joining on YouTube. Again, keep in mind, it's support from the sponsors and you that allow me to work on TOE full time. You also get early access to ad-free episodes, whether it's audio or video. It's audio in the case of Patreon, video in the case of YouTube. For instance, this episode that you're listening to right now was released a few days earlier. Every dollar helps far more than you think. Either way, your viewership is generosity enough. Thank you so much.